All right, so let's do a classic problem here. I have let's make it a 10-meter stick and 15 kilograms. So it's 10 meters long, that's 10 meters, 15 kilograms. I have a force holding up here, a force holding up here. Let's assume uniform density. And so I have some force F1, some force F2. And I want to be able to figure out what are the two forces that are holding it up. So I have ground, earth down here. So if we did a force diagram, because you never quite get away from it, we have the weight acting down in the middle, because the uniform density is telling me it's evenly distributed, so the weight is acting down in the middle. Oh, I need to tell you how far that is. Let's make that 1 meter, and let's make that 2 meters. Obviously not drawn to scale. Therefore, the distance in between them would be 7 meters. So I have this force F1 acting up here, weight acting down, and then I have F2 acting up. Now, it is an equilibrium. And we have two types of equilibrium. We've talked about static and dynamic equilibrium in the past, but now we're talking about linear and rotational equilibrium. So linear equilibrium is acceleration is 0. Rotational equilibrium means the angular acceleration is 0, or total torque is 0. So I know that F1 plus F2, let's establish our I, J, and K. So F1 plus F2 minus W equals 0. And then there are no forces in the I direction, so there's no I equation, but I do have a K equation. I have torque. Now, in order to know what the torque is, I need a pivot point. With a door, it's very clear what the rotational axis is. It's the hinges. But for other things, for something in rotational equilibrium, it's not readily obvious. All right, so we did the sum of the forces as mass times acceleration, so now we're going to do the sum of the torques is equal to I times alpha. And I know it's 0 because it's in rotational equilibrium. There's no angular acceleration. It's not rotating anyway about any pivot point. Now, since it doesn't have a pivot point, because remember, torque is R cross F, this R is known as the moment arm. It is a vector from the pivot point to where the force is applied. And if there's no pivot point, what do you pick? If there's no natural pivot point, what do you pick? Well, you pick anything that you want. Now, some people will pick spots on the ends, which are natural points, and some people will pick points where the forces are. And you can even pick a point off site here. It doesn't really matter. I'm going to pick this point right here as my pivot point. And so then I have 3 forces, so potentially I have 3 torques. Well, the first one, the moment arm, a vector from the pivot point to where the force is applied. So that is a 0 vector. Cross the force, so that is in the J direction. Plus, so that's 0, whatever direction you want. Plus the torque from this one. Well, the R vector is from the pivot point to where the force is applied. And so since force 1 is 1 meter from the end and the center is 5 meters from the end, this distance here is 4 meters. So this would be 4 meters I hat cross my force, which is negative mg j hat, negative j hat because it's going down and I said up was positive, plus the torque from this vector right here. Well, that distance there is 7 meters as discussed earlier. And so we have 7 meters I hat because it's a vector going to the right cross F2 j hat. And that's equal to 0. So that's 0. This we're left with negative 4 mg. Recognize this m here is meters. This m right here is mass. So we have 4 mg I cross negative j. Sorry, we have the negative sign there. I cross j. Plus this over here, which is 7f2 I cross j equals 0. I cross j is k, so I got negative 4 mgk plus 7f2k equals 0. I have negative 4 mg plus 7f2 times k hat equals 0. In other words, this has to equal 0. So mathematically, I have negative 4m, and I know what the mass is, and I know what g is. Let's assume it takes place on Earth. There's my mass. mg is 15 times 9.8, which is 147. So I have negative 4 times 147 plus 7f2 equals 0. So 7f2 is equal to whatever that is. 8, 15. All right, that part was right. 4 times 588 equals 588. So F2 divided by 7 is 84 newtons. So I know this now is 84 newtons. I can now go into this equation over here. This is 84. So F1 plus 84 minus 147 equals 0. And so F1 is equal to 147, 63 newtons. So 63 newtons. Now notice that in terms of distance, this is 4 meters here, and this is 3 meters here. The force that's closer to the actual weight has a greater force. It's 84 newtons versus the 63 newtons. But that's just a classic equilibrium problem. But we can make it more interesting. And that's for a different video.